e to the x properties and the derivative. So let's start by solving exponential and logarithmic equations. We've got 7 equals e to the x plus 1 power. Since x is up in the exponent, we need to somehow break it out of there. In order to undo the e to the whatever power, we're going to take the natural log of both sides of this equation. So left side is natural log of 7 equals right side natural log of e to the x plus 1 power. There's a log property that says that if your argument, like e, is to an exponent, like x plus 1, you can take that exponent and put it in front of your natural log. So we've got natural log of 7 equals x plus 1 times the natural log of e. Okay. The natural log is the log of base e. So if this is also an e, this kind of cancels out to become just 1. That's because natural log and e are inverse functions of each other. So if this reduces to 1, we're left with natural log of 7 equals x plus 1. Our goal is to get x by itself to figure out what x equals, so we can subtract 1 from both sides. Natural log of 7 minus 1 equals x. Now, natural log of 7 is a constant number. There's no x's or other variables in here. So this is natural log of 7 minus 1. This does not become natural log of 6. The 1 does not get subtracted in here. Number 2. Kind of the opposite, but a similar thing. We've got x that is inside the argument of a natural log instead of being inside of an exponent. We still have to use the fact that natural log and e to the whatever power are inverse operations of each other. So we can take e to the and e to the on both sides. Natural log of 2x minus 3 and 5, since they are equal to each other, e to the natural log of 2x minus 3 and e to the 5 are equal to each other as well. All right, e to the natural log of that, since e and natural log are inverse operations of each other, we're just left with 2x minus 3 equals. Then we bring down e to the 5th power. Again, e to the 5th is a constant. You can find that number in your calculator. It is an awful looking decimal, but it is a number. We can solve for x now by adding 3 and dividing by 2. 2x equals e to the 5th plus 3, and then divide both sides by 2. X equals e to the 5th plus 3, all of that over 2. X is by itself, so that is our answer. Let's do a review of some exponent rules. So these are things that you learned back in like Algebra 1, e to the a times e to the b. This is similar to when you did back in Algebra 1, like x squared times x cubed. That's the same thing as x to the 5th power. And you get that 5 by adding those two exponents together. You can do the same thing with e's. As long as the bases are the same and these are multiplied, you add the exponents together. So it becomes e to the a plus b power. You can do that if a and b are both constants. If they are both variables, you can do it if one is a variable and one is a constant. You have lots and lots of options. Number 2, e to the a over e to the b. This is the same thing as e to the a minus b, right? You take the top exponent and subtract the bottom exponent. Let's do some examples. We've got e to the 4th times e squared. That would be e to the 6th power after adding those two exponents together. The fraction, e to the 5th over e squared. That is the same thing as e to the 5 minus 2 is 3. E over e to the 5th, that is e to the 1st over e to the 5th. This becomes e to the negative 4, which of course is 1 over e to the 4th power. Last one, e to the 0 power. This is the one that's going to show up the most often because anything to the 0 power just equals 1. Down here are some properties of the natural exponential function, which is the e to the x. So if we have the function f of x equals e to the x, this is our information. Let's start out with a graph. Move to the side and just draw a graph at the end here. It's our x-axis and our y-axis. E to the x goes through the point 0, 1. It starts out like really close to the x-axis, goes through 0, 1, and then goes up very quickly because it's an exponential function. Information we can get from this. Our domain, since we have an arrow pointing left and an arrow pointing right and our graph is continuous, our domain is negative infinity to positive infinity. Our range is what is the lowest y value to the highest y value. The lowest our graph goes is it gets really close to the x-axis, which means that we have a horizontal asymptote, horizontal asymptote at y equals 0. E to the x will never equal 0. It can only equal positive numbers. So that means that the range is 0 to positive infinity. Cannot touch 0, so we have a parenthesis, and then infinities always get parentheses. Okay. E to the x is always increasing, which means it always goes up as you go to the right, and e to the x is continuous. It is continuous and increasing. Number 3, e to the x is concave up on its entire domain. We'll talk about concave up and concave down in a different section, but we definitely want it in these notes so we can come back to it at some other point. Number 4, limits as x goes to negative infinity and positive infinity. That's just end behavior. So this is the left end behavior, and this is the right end behavior. To the right, our y values go up forever. So positive infinity for x goes towards infinity. As x goes towards negative infinity, we are getting really close to the y value of 0. So left end behavior is 0 because the horizontal asymptote at y equals 0. And there is no limit on the right-hand side, so positive infinity because it's going up. The derivative of the natural exponential function. This derivative is going to make you very happy because it is super duper easy. E to the x's derivative is just e to the x. Yay. We get a little bit more complicated when the exponent is not just an x, it's another function. We have to use the chain rule. So the derivative of e to the u is e to the u times u prime. You just take the derivative of whatever the exponent is. Now it's going to be pretty common that your u prime is going to be just a number, and it's going to look a little bit nicer and cleaner if you put whatever that derivative is first times e to the u power. So this is technically the rule for it. Usually you'll write your answer this way. Number 1, we want to take the derivative with respect to x of e to the 2x minus 1. 2x minus 1 is u, right? It's the exponent. Its derivative, u prime, is just 2. We can use the power rule from way back when we first learned derivatives. So the derivative with respect to x of e to the 2x minus 1 is e to the 2x minus 1 times u prime, which is 2. It definitely looks cleaner if you put the 2 first and then the e to the 2x minus 1. You can put multiply in there if you want. It's just kind of understood. Number 2, the derivative with respect to x of e to the negative 3 over x. U in this case is negative 3 over x. And we want u prime. Instead of using a quotient rule, we would prefer to rewrite this as negative 3x to the negative 1 so that we can use the power rule. Using the power rule, negative 3x to the negative 1 has a derivative of 3x to the negative 2. And let's go ahead and rewrite that right now before we bring it into our derivative for the actual answer. So this is all of our side work. U prime then would equal 3 over x squared. Okay, so the derivative with respect to x of e to the negative 3 over x is e to the negative 3 over x times 3 over x squared. There's maybe some better ways to write this. I'm going to put e to the negative 3 over x over the x squared, right? Put the x squared on the bottom, and then just put the 3 in the front. You might also notice that e has a negative exponent and decide that you really want to put that e in the denominator and give it a positive exponent. So let's try that. This would equal 3 over x squared times e to the 3 over x. So any of these options is a viable answer, which means that any of them could show up on multiple choice, and you just have to understand that they're equivalent to each other. Number 3, the derivative with respect to x of e to the 4x times x squared. This is a product rule problem. So we'll have to take the derivative of x squared and the derivative of e to the 4x and kind of work around with this stuff. Okay, let's make x squared be the first function. So I'm going to put all of its stuff in yellow. And e to the 4x, let's do that in green. Okay, product rule says we have multiply, add, multiply. We take the derivative of x squared and get 2x. And then we keep e to the 4x. Plus, keep x squared and multiply by the derivative of e to the 4x. Okay, so now we're going to need u and u prime for that e to the 4x. U equals 4x. U prime just equals 4. So our derivative is going to be e to the u, is e to the 4x still, times u prime, which is 4. Now, you can leave the 4 where it is, or you can choose to put the 4 here instead, kind of like the 2 is to the left of the x. So to clean it up just a little bit, 2x e to the 4x plus 4x squared e to the 4x. Looks a little bit cleaner, but it doesn't matter again. We have an example that is a word problem. The projected population Y in thousands of California from 2015 through 2030 can be modeled by Y equals 34,696 e to the 0.0097 t. T represents the year, and t equals 15 represents 2015. Okay, so it looks like we're just looking at the tens and ones digits. At what rate will the population be changing in 2020? Okay, so we're looking for what is the rate of change of the population. Y is the population, so we're looking for the rate of change of y, which is just y prime. Y prime is going to be the derivative of this e function. So that's 34,696 e to the 0.0097 t times whatever u prime is, right? This is e to the u times u prime. And this 34,000 bit is just the coefficient that was already there. So we just really need the derivative of u. This is u, the derivative is 0.0097. Now we're going to clean that up a little bit. Y prime equals, we multiplied 0.0097 times that 34,696, and we get 336.5512. Use a calculator to multiply that decimal times this 34,000. So this is the rate of change of the population at any time t in our domain, and our domain is 2015 through 2030. We want to know what is the rate of change of population in 2020, which means t would have to equal 20. Y prime equals 336.5512 e to the 0.0097 times 20. Notice that this multiplication happened in line with this. This multiplication is multiplied times the exponent, okay, because 20, that t was part of the exponent. Make sure in your calculator that if you have, if your calculator does the e to the, that you put all of that in there, including the times 20 before you put in your parentheses, so it knows that the 20 is part of the exponent, not multiplied times this bit. Okay, so that's in the older versions of the calculator. That erased beautifully. Alrighty. Plugging that into the calculator, we end up with y prime equals 408.6055, blah, blah, blah. 3 decimal places gives us 0.606. Let's write a sentence. Since t is time, we definitely want to start our sentence with something involving the year, the time. You could say at t equals 20, or you could say in 2020, or in the year 2020, or something like that. So let's say right now. At what rate will the population be changing? So the population is the thing that was changing. The population of California is, you have to say increasing or decreasing. Since the 408 was positive, we're going to say increasing at a rate of 408.606. Okay, Y was measured in thousands of people, so 1,000 people per, because it's a rate, so there's going to be a change in time as well. T was measured in years, so per year. So there's an increase of about 408.606 thousand people, 408,606 people per year of a population increase. That's quite a bit, quite a few people. All right, example down here, determine dy dx for the function y squared equals 2e to the xy. Okay, we need to do implicit differentiation on this problem because we cannot get y completely by itself. There is a y in the exponent, and there's also a y over here in this base. We have to take derivatives of both sides with respect to x. Our goal is to get dy dx completely by itself. So we've definitely done problems like this back in implicit differentiation. We just haven't had problems with e to the whatever power yet. All right, so let's take derivatives. Derivative of y squared is 2y times dy dx, right? Every time you take a derivative when there was a y, you got to toss that dy dx in there as well. Okay, over here, 2e to the xy. Well, that's e to the u. Let's do that u thing off to the side. U equals x times y. If that is multiplication, then u prime is going to need a product rule. Okay, derivative of x is just 1, keep the y, plus keep the x, take the derivative of y, which is dy dx. That was our side work. Alrighty, over here, 2 times e to the, keep the xy, right, e to the u, times u prime. U prime is y plus x dy dx. Okay. The goal that we had was to get dy dx completely by itself. There's currently dy dx is on both sides of the equation, so it's definitely not by itself. And also the dy dx is inside a set of parentheses. So how can we simplify that right-hand side so that we can get this term over to the other side? You cannot currently subtract this over because there is multiplication. It's inside a set of parentheses. So we're going to take the outside term, or I'm sorry, the outside factor, which is 2e to the xy, and distribute it into the y and to the x dy dx. Now notice where I put that, the 2e to the xy. So I've got 2y dy dx. I'm distributing. I'm going to put the 2 first, and then the y, and then the e to the xy. Plus, because of that plus. Again, 2. X. E to the xy. Dy dx. There's kind of like an order to writing all of this stuff out, like grammatically, mathematically. We want the coefficient number in front, and then any just variables, and then anything within e to the exponent, anything that's exponential, and then finally you want your dy dx bit to be at the end. The same kind of order went for this guy, but there was no dy dx to be at the end. The same order for the left, except there was no e to the anything. Zoom out a little so we can see the whole thing. Our goal is to get dy dx all onto one side so that we can eventually get dy dx by itself. So we're going to subtract this whole term over here over to the left. We got 2y dy dx minus 2x e to the xy dy dx equals this term 2y e to the xy. You guys might notice that there is a 2 as a coefficient in every single term. We can cancel that out kind of whenever you need it for your derivative to show that you had it and that you took your derivative correctly. But at this point, like, we can just kind of cross them out. Divide both sides by 2. Boom, gone. All right, we want dy dx by itself. We've got to factor out dy dx in that case. Dy dx factored y minus x e to the xy. The right side is y times e to the xy. Then dy dx is still not by itself. It's multiplied times the parentheses, so we'll divide both sides by the parentheses. Dy dx equals top y e to the xy over parentheses y minus x e to the xy. This is our answer because dy dx is by itself. There was no way to get y by itself in the original problem, so you do not have to substitute out the y's for something else.